Imagine building a future home on Mars, only for it to be swallowed by a colossal dust storm. Are these Martian tempests merely atmospheric disturbances, or do they hold the terrifying power to strip away any hope of a habitable future? We're diving deep into the true impact of Mars's most enigmatic weather. Forget everything you thought you knew about living on Mars. The planet's iconic dust storms aren't just a pretty picture, they could be the single biggest barrier to human survival. Discover why the dream of a Martian colony might just be a cosmic mirage, and what that means for humanity's future. Right now, what if the dream of a new home among the stars was constantly under attack? For years, Mars has tantalized us with the promise of a second chance, but its relentless dust storms tell a different story. Join us as we uncover the unsettling truth. Is Mars truly a future home, or just a beautiful, yet deadly, illusion? Begin with a stunning visual of Mars, then quickly introduce the romanticized idea of Mars as our future home versus the harsh reality of its current state. Imagine the planet suspended in the velvet blackness of space, its rusty deserts glowing faintly as sunlight brushes across its cold plains, giving the impression of a world both inviting and mysterious. Yet beneath this beautiful facade lies a realm far more unforgiving than most dreamers imagine, for while movies and stories often paint Mars as a canvas ready for human footprints and thriving domes, its reality is a hostile stage defined by bitter winds, poisonous dust, and air far too thin for life from Earth to breathe. This tension between fantasy and truth creates a powerful opening moment, drawing the listener into a deeper, slower exploration of Mars as it truly is, rather than as we wish it to be. The romantic image of Mars has been shaped for decades by science fiction covers glowing with futuristic cities and heroic colonists striding across red dunes, but when we peel back the imaginative varnish, a harsher tale emerges, one where the cold is so intense it sinks through metal, and where the sunlight is only half as strong as Earth's, casting long, pale shadows that stretch across landscapes carved by ancient catastrophes. People often imagine Mars as dusty but manageable, barren but workable, yet the truth is that stepping outside without protection would freeze your blood in minutes, and the whispers of wind would not comfort but scour, carrying tiny grains sharp enough to erode equipment over time. This clash between the dream and the reality is where the story truly begins, a reminder that the red planet is beautiful not because it is ready for us, but because it remains stubbornly alien, untouched, and unsoftened. As our gaze lingers on the planet's rugged surface, the first thing that becomes apparent is the sheer emptiness. No oceans glimmer, no forests sway, no rivers carve their paths across the land. Instead, colossal canyons stretch for thousands of kilometers, and volcanoes loom taller than any mountain range on Earth, their slopes ancient and silent, reminders of a world that once had fire in its heart but now lies subdued and cold. Those who dream of settling Mars often imagine wide, open plains where habitats can be placed like outposts on a frontier, but standing on the surface would feel more like being on a frozen desert where the ground holds secrets from billions of years ago. The silence is not peaceful in a comforting sense, it is heavy, absolute, a silence that swallows sound rather than welcomes it. The first breath you would instinctively try to take would never come, for the atmosphere of Mars is so thin that it would feel like standing near the top of Earth's highest mountains but without the mercy of any oxygen. The air is mostly carbon dioxide, and the pressure is barely 1% of Earth's, meaning that your lungs would find nothing to cling to, nothing to draw from. In stories, explorers on Mars often jog across dunes as if the environment is simply inconvenient, but in truth, even with a pressurized suit, every movement must be deliberate, slow, measured, because the world around you gives nothing freely. The romantic idea of fresh starts and new horizons must confront this physical truth. Mars cannot sustain us without layers of technology between our bodies and the environment. Despite these harsh realities, the allure persists, in part because Mars feels like the closest relative to Earth among the planets, a world with mountains, seasons, polar caps, and evidence of ancient rivers. But those features are relics of a past far different from today, a past when the planet may have been warmer and wetter, shaped by flowing water rather than relentless dust. When we imagine building cities on Mars, we draw from this ancient memory embedded in its rocks, forgetting that the world we see now is one where liquid water cannot survive on the surface without evaporating instantly. To call Mars a future home requires confronting the reality that any thriving environment we build there will be artificial, constructed with immense effort and constant maintenance. The planet's dust, fine, pervasive, and electrostatically clingy, is one of its most troublesome features, far more than most dreamers anticipate. It infiltrates machinery, sticks to suits, scratches solar panels, and carries chemicals like perchlorates that would be toxic if inhaled or allowed to contaminate water supplies. When settlers in stories stride across Martian dunes, their footprints crisp against the surface, it seems almost poetic, but real dust storms can envelop the entire planet for weeks at a time, reducing sunlight to a faint glow and making solar systems almost useless. The romantic vision of majestic storms swirling across the horizon becomes, in reality, a reminder of how fragile any human presence there would be. Temperature on Mars is another disquieting truth. While the equator may experience moments of relative warmth during midday, enough to trick the imagination, most of the planet remains bitterly cold, with nights plunging far below freezing. Materials shrink and expand, electronics struggle, and exposed water freezes instantly. Dreamers often imagine Martian sunsets as warm, gentle affairs, the sky glowing with soft colors, but even these beautiful spectacles are accompanied by a cold so penetrating it feels more like stepping into the vacuum of space than being on a planet's surface. The romance of Mars dims slightly when one realizes how constantly humans would need to fight against the cold. Some viewers see Mars as a blank canvas where humanity might escape the problems of Earth, but this perspective overlooks the complexity of starting a civilization where nothing grows naturally. Farming on Mars would require carefully controlled environments, artificial lighting, radiation shielding, and constant monitoring of soil that contains chemicals harmful to plant life. The dream of planting the first Martian garden under a transparent dome becomes more technically demanding than emotionally uplifting, as every leaf would depend on life support systems never allowed to fail. This transforms the romantic fantasy into a slow, meticulous reality where survival outweighs sensation. Radiation is another challenge that rarely appears in the beautiful illustrations of Mars colonization. Without a global magnetic field and with only a thin atmosphere, Mars is constantly bombarded by cosmic rays and solar particles. On Earth, we are shielded by layers of protection that allow life to thrive on the surface, but on Mars, settlers would need to live underground or beneath layers of regolith to avoid long-term damage. The idea of waking up in a cozy habitat with a window overlooking the dunes sounds peaceful, yet in truth, those windows would remain mostly for short visits rather than daily living, as radiation quietly accumulates with each moment spent exposed. Even communication between Mars and Earth is a reminder of distance, as signals take anywhere from 3 to 22 minutes to travel one direction depending on the planet's positions. People imagine calling home like explorers on Earth, but conversations would be filled with long pauses, delayed reactions, and a sense of emotional distance that no technology can bridge instantly. Messages become more like letters than conversations, creating a rhythm of communication that feels slower and more distant than our world of instantaneous connections. This difference subtly shifts the dream of living on Mars into something quieter, more introspective, and more isolating. Gravity on Mars, only about 38% of Earth's, would feel strange, almost playful at first, but over time it could cause health problems that researchers still do not fully understand. Muscles weaken, bones lose density, and the human body, calibrated for Earth's pull, must adapt in ways that might not be fully reversible. People often imagine bounding across the Martian surface with ease, but living long-term in reduced gravity might mean a lifetime of medical adjustments and careful exercise routines designed to keep the body from deteriorating. The romance of movement becomes another scientifically managed aspect of daily life. Water, essential for every breath, crop, and human cell, exists on Mars mostly as ice, locked beneath the surface or trapped in the polar caps. Extracting it requires machinery, energy, and patience, and any contamination from Martian chemicals poses a serious risk. While dreamers envision settlers melting ice into clean, fresh water for their habitats, in reality the process would be laborious, expensive, and delicate, with each drop representing the effort of complex engineering systems working in harmony. Water, so abundant on Earth, becomes a precious resource that shapes every aspect of life on Mars. The idea of walking outside to enjoy a breeze or touch the soil with bare hands fades quickly when considering that Martian air cannot sustain life, and touching the soil without protection exposes one to harmful chemicals. Gardens must be sealed, climates must be regulated, and every interaction with the outside world requires layers of equipment. This transforms Mars from a place of open exploration into a world where the indoors becomes a fortress, and the outdoors a landscape visited with caution rather than ease. Even the soundscape of Mars differs from romantic expectations. The thin atmosphere carries sound poorly, muffling everything into faint whispers. A footstep, a tap on a rock, or a shouted call would sound distant and muted. The dream of hearing the wind sing across the dunes becomes a quiet, hollow hiss, a reminder that Mars is not a world built for human senses. This difference may seem small, but over time it shapes how settlers would feel, think, and perceive their environment. Nightfall on Mars introduces another layer of quiet strangeness. Without a thick atmosphere, the stars blaze with clarity, and the moons, Phobos and Deimos, rise with eerie brightness, moving quickly across the sky. It is beautiful, yes, but also unsettling, for the familiar rhythms of Earth vanish, replaced by a sky that feels both breathtakingly open and profoundly empty. Settlers viewing the night sky through thick windows would see beauty, but also distance, an ever-present reminder of how far they are from home. Despite all these challenges, the idea of Mars retains its magnetism because it represents something deeper, the human desire to explore, to expand, and to find meaning beyond the world we already know. But to honor that desire requires respecting the reality of Mars as a world that demands resilience, patience, and humility. Romantic images may spark the journey, but truth sustains it. When we picture building habitats on Mars, we imagine clean structures gleaming under the red sun, but in practice these shelters must withstand dust abrasion, temperature swings, and radiation. They become more like fortresses than homes, and maintaining them becomes a constant task. The dream of strolling between domes in the open air fades, replaced by careful, pressurized walks guided by strict safety protocols. Beauty exists, but it sits within limits that must be respected. Even transportation on Mars is a challenge. Rovers must be sealed, heated, and meticulously monitored for power and wear. A simple journey across a dusty plain becomes an orchestrated mission requiring checklists, backups, and caution. The excitement of exploration gives way to a slower, steadier pace, one where every kilometer traveled requires planning and disciplined awareness. The romance of road trips becomes a calculated journey through a hostile environment. Terraforming, often depicted in fiction as a grand transformation, is far more difficult than many imagine. Thickening the atmosphere, warming the climate, and creating conditions where water can flow are tasks that require centuries, not decades, and might not even be possible with current physics and planetary limitations. The idea of turning Mars into a second Earth is poetic, but grounded truths suggest a planet resistant to such change, requiring technologies far beyond what we currently possess. Psychologically, living on Mars would mean adapting not only to environmental challenges but also to the emotional weight of isolation, confinement, and the constant awareness of fragility. Each day, settlers would move through environments where failure is not merely inconvenient but life-threatening. The romanticism of adventure must be balanced by the mental resilience needed to thrive in such conditions, where comfort is engineered and nature remains distant. Yet, even with all these barriers, Mars continues to call to us. Its landscapes, alien yet familiar, awaken something ancient within the human spirit, a desire to reach out, to learn, to endure. The planet's silence invites contemplation, its vastness inspires reflection, and its history whispers possibilities about what it once was and what it might become. The dream of Mars persists not because it is easy, but because it is hard, because the gap between longing and reality challenges us to grow. And so, the romance of Mars does not die when confronted with its harshness. Instead, it evolves. It shifts from a fantasy of effortless colonization to a deeper appreciation of what it would truly mean to live on another world, one where beauty is intertwined with danger, and where every sunrise over the red horizon becomes a testament to human determination. This is the true story of Mars, a world not waiting for us, but daring us to understand it fully before we try to make it our own. Briefly touch upon the historical fascination with Mars and how early observations fueled dreams of a habitable world. For centuries, the tiny red dot drifting across the night sky stirred human imagination, offering a sense of mystery that seemed to demand explanation. Ancient astronomers, watching its steady march through the heavens, recognized that Mars behaved differently from the fixed stars, marking it as something more meaningful, more dynamic. By the time telescopes came into use, those blurry reddish hints transformed into more distinct shapes and shadows that appeared to shift with the seasons. These early glimpses made people wonder whether Mars might be a living world, one with weather, landscapes, and perhaps even civilizations waiting beyond visibility. The line between observation and imagination blurred, forming the roots of a fascination that would grow for generations. When telescopes improved in the 19th century, astronomers began mapping features that seemed to resemble coastlines, patches of vegetation, and most famously, straight lines stretching across the planet's surface. These so-called canali, sketched by Giovanni Schiaparelli, were mistranslated as canals, igniting the belief that intelligent beings might exist on Mars, engineering vast waterworks to survive a drying planet. The idea spread quickly, capturing the public's imagination and redefining Mars not as a barren world but a fading oasis nurtured by advanced minds. Though the truth was far simpler, misinterpreted imagery and optical illusions, the belief endured long enough to shape an entire era of speculation and wonder. Writers like Percival Lowell built upon these early maps, devoting years to meticulous observations and producing detailed drawings of networks of canals crisscrossing the Martian globe. For Lowell, these weren't just natural features, they were evidence of a noble civilization clinging to survival. His vivid writings blended scientific curiosity with romantic interpretation, persuading the public that Mars was a dying but still inhabited world. Fiction writers, inspired by Lowell's confidence, began crafting tales of Martians with advanced technologies and entire cultures built upon the management of dwindling resources. This interplay between science and imagination deepened the fascination, transforming Mars into a canvas for speculation about alien life. The late 19th and early 20th centuries saw even more stories emerge, each adding layers to the imagined identity of Mars. H.G. Wells, for instance, offered a much darker interpretation with The War of the Worlds, imagining Martians as conquerors seeking new territory after exhausting their own world. This flipping of perspective pushed the public to think about Mars not just as a place to discover but as a potential threat, reflecting both fear and awe. Mars became a mirror where humanity projected its hopes, anxieties, and dreams, shaping cultural imagination in ways that surpassed other planets. It became our cosmic neighbor not just physically but emotionally. As technology progressed, scientists discovered seasonal changes in Martian color patterns, especially the darkening and lightening regions that seemed to shift with the Martian seasons. Many interpreted these changes as vegetation cycles, imagining hardy plants spreading across the planet during warmer months. Though later understood as dust redistribution rather than biological growth, these early interpretations strengthened the belief that Mars might still harbor life. The excitement was not just scientific, it was emotional, a longing for connection beyond Earth, for confirmation that humanity was not alone in the vast universe. Even speculative maps of Mars circulated widely, illustrating continents, seas, and icy caps reminiscent of Earth's geography. For many, this suggested that Mars had undergone similar geological processes, further supporting the dream of a habitable world. People looked at these sketches and envisioned explorers crossing Martian deserts, uncovering lost cities, or meeting alien cultures. The more details artists added, the easier it became to imagine Mars as a place not unlike Earth, a world with weather, landscapes, stories, and history. This illusion persisted long before spacecraft shattered the dream. The early 20th century saw continued scientific debate about the canals and alleged biological changes. Major observatories across the world dedicated countless hours to observing Mars, straining to discern finer details beneath atmospheric distortion. Some astronomers argued passionately for natural explanations, while others fought to keep the idea of life alive. This debate fueled newspapers and public lectures, embedding Mars deeply into popular culture. People attended sky-viewing events in droves, peering through telescopes and believing they were glimpsing another inhabited world. Mars became a shared cultural fascination. The arrival of radio signals added a new dimension to the mystery when some researchers speculated that unusual cosmic static might be attempts at communication. Although these theories were later dismissed, they intensified public belief that Mars might harbor intelligent beings. For a time, amateur groups began scanning radio bands, hoping to intercept messages from Martians. Even though no such signals existed, the very idea of listening for voices from another world kept the dream alive. Curiosity mixed with hope in a powerful blend that persisted all the way into the mid-20th century. Hollywood embraced these ideas, producing films that portrayed Mars as everything from a dying planet ruled by fragile, ancient beings to a bustling world of futuristic cities. These stories held incredible influence, shaping how entire generations imagined the Red Planet. Mars became a backdrop for emotion, adventure, fear, romance, and discovery. Viewers came to believe, even if subconsciously, that Mars must hold some secret, some life, or at least some narrative that humanity had yet to uncover. Science and storytelling intertwined so tightly that separating fact from fiction became nearly impossible for the average person. Children growing up during that era often saw Mars as the first destination in humanity's future among the stars. Science fair posters depicted rockets landing on Martian plains, explorers erecting bases, and astronauts gazing across dunes of red sand. This early optimism made Mars feel accessible and near, a place where future societies might flourish. Even when scientific evidence did not fully support these hopes, the cultural momentum was strong enough to keep them alive. Mars, in the minds of many, was not barren, it was waiting. The fascination deepened when astronomers discovered polar ice caps on Mars, bright, glistening, and visibly shrinking and growing with the seasons. These icy features mirrored Earth in a way few celestial objects did. People imagined vast frozen oceans lying beneath the surface, harboring ancient creatures or preserving remnants of past civilizations. Even though scientific understanding has since clarified their nature, those early interpretations pushed the idea of Mars as a dynamic, evolving world rather than a static, dead sphere. Some early researchers hypothesized that Mars might still retain underground reservoirs of liquid water, even when surface conditions seemed too harsh for it. This idea opened the door to speculation that microbial life, or even more complex forms, could exist beneath the planet's crust. While evidence remained elusive, The possibility alone kept Mars at the forefront of astrobiological curiosity. People imagined hidden caverns, warmed by geothermal heat, sustaining ecosystems where sunlight failed to reach. The notion that life might cling to the planet's interior nourished dreams of discovery. As telescopes improved further, the so-called wave of darkening, a seasonal phenomenon, led some to propose that plants were blooming across the Martian landscape each spring. Though incorrect, the theory spread widely, giving Mars the appearance of a world that breathed, rested, and awakened just as Earth did. A living planet, even if sparsely populated, was far more emotionally appealing than a dead one. The public embraced this interpretation eagerly, transforming Mars into a symbol of resilience and adaptation in an unforgiving universe. This fascination persisted into the era of spaceflight, long before any spacecraft reached Mars. Early mission planners often spoke of Mars as the obvious next step after the Moon, partly because cultural narratives had made it feel more familiar than other planets. When rockets launched skyward, people watched with the hope that soon humanity would uncover the secrets of the Red World. The idea that Mars was special, perhaps even meaningful in some way, continued to shape enthusiasm for exploration. The belief in a habitable or once habitable Mars also influenced scientific institutions. Research centers funded studies on Martian climate, geography, and possible biology. Whole conferences were devoted to Mars long before we had clear images of the surface. This dedication reflected a deeper belief that Mars held answers about life itself, about how it emerges, evolves, and perhaps even disappears. The possibility that Mars once resembled Earth made it a kind of cosmic time capsule, drawing researchers like moths to flame. As the space age approached, artists produced iconic concept art showing landers touching down on rocky plains, astronauts raising flags, and domes glowing beneath a dim sun. These images were compelling not because they were accurate, but because they embraced the long-standing dream that Mars could be humanity's second home. They connected modern technology with ancient imagination, creating a seamless narrative of human expansion. Even before the first robotic probe arrived, the public felt emotionally invested in the planet. Schools taught children about Mars as a world of mystery and possibility. Textbooks speculated openly about life, climate, and even ancient civilizations. Students drew pictures of Martians and landscapes filled with strange plants or towering cities, merging scientific curiosity with creativity. These early impressions often shaped lifelong interests and ambitions, inspiring future scientists, engineers, and writers. Mars became a place where imagination blended with education, making it both magical and approachable. Philosophers and thinkers also pondered the moral and existential implications of life on Mars. Some argued that discovering Martian organisms would reshape humanity's understanding of its place in the cosmos, while others believed Martians, if they existed, would force us to reconsider ethics beyond Earth. Even without evidence, these discussions thrived because Mars felt close enough, familiar enough, and mysterious enough to evoke profound reflection. It became not just a world to explore but an idea to contemplate. Even early radio dramatizations contributed to the fascination, famously causing panic during the broadcast of the War of the Worlds. Listeners believed Martians were invading Earth, which demonstrated how deeply embedded Mars had become in public consciousness. The idea that people could react so intensely to fictional Martians underscored how real Mars felt emotionally. It was no longer merely a planet, it was a cultural presence, a symbol of the unknown. By the time the first spacecraft finally reached Mars, expectations were sky-high. Many hoped to see canals, forests, or at least signs of a once thriving civilization. The photographs that arrived, bleak and barren, shocked many. But even the disappointment could not erase centuries of fascination. Instead, it redirected curiosity, shifting the narrative from imagined civilizations to the scientific mystery of a planet that once seemed alive but now lay silent. The early misconception of Mars as a habitable or inhabited world, though scientifically inaccurate, created a powerful momentum that shaped everything from literature and philosophy to space policy and technology. It wasn't the truth of Mars that captivated humanity, it was the possibility. That possibility fueled dreams, inspired exploration, and built a foundation upon which modern Mars science still stands today. The fascination persists because the longing behind it never fully fades. In the end, early observations did more than mislead, they awakened humanity to the idea that other worlds might hold stories worth discovering. Even once the canals vanished and the vegetation theories dissolved, the emotional weight of those fantasies lingered. Mars remains a world where hope, wonder, and curiosity collide, reminding us that sometimes the dream itself becomes the spark that drives true discovery. Transition to the dramatic impact of Martian dust storms, showcasing their scale and power through visuals and data. Imagine the camera drifting downward from the tranquil orbit of Mars, where the planet appears peaceful and calm, its red plains shimmering softly beneath thin sunlight. But as the lens glides closer, a curtain of swirling particles begins to rise, revealing the true force that dominates Martian weather, dust storms of staggering magnitude. These storms are not gentle breezes carrying harmless grit, they are vast, roiling systems capable of engulfing entire regions, smothering landscapes in a haze so dense that day becomes as dim as twilight. Visuals would capture towering walls of dust stretching for kilometers, moving with a silent but immense presence. Data overlays could display their span, sometimes exceeding millions of square kilometers, illustrating that these storms are not rare events but recurring, planet-shaping phenomena that define Mars more powerfully than any other atmospheric process. From the surface, the approach of such a storm would look almost apocalyptic, a rolling frontier of suspended minerals that creeps and expands until the horizon vanishes. Unlike Earth's storms, where clouds tower and winds howl, Martian storms possess a haunting subtlety. Though the atmosphere is thin, the dust remains suspended due to electrostatic charging and persistent winds that whip across the plains. Instruments have measured that even moderate storms can lift particles high into the atmosphere, reflecting sunlight and altering temperatures across the globe. The visuals might show delicate grains rising in slow motion, emphasizing that despite their lightness, they accumulate into something powerful enough to cloak the entire planet in a single, swirling shroud. While the winds of Mars are not as forceful as hurricanes on Earth, the low gravity and small particle size allow dust to spread rapidly across vast distances. Even breezes of tens of meters per second can stir up immense clouds that obscure valleys, dunes, and crater basins. Footage could illustrate how a storm begins in a single region, perhaps triggered by temperature contrasts near the equator, and then spirals outward, gaining momentum until it crosses hemispheres. Detailed simulations could visualize how a local storm transforms into a regional event, then a continent-spanning one, and finally into a global storm that envelops virtually every corner of the planet. Such transitions give Mars a dynamic, almost volatile personality that contrasts sharply with its otherwise quiet environment. The opacity of these storms is one of their most striking characteristics. During major events, sunlight can drop to just a few % of its normal brightness. Robotic explorers like Opportunity, which once relied on solar power, struggled under these conditions as dust accumulated on panels and blocked vital energy. Visuals could fade from bright, crisp images of the Martian terrain to dim, sepia-toned scenes where shapes blur and shadows vanish. Data indicating decreasing solar energy or plunging temperatures could appear alongside these visuals, illustrating just how dramatically conditions change during such storms. Despite the dramatic reduction in light, the temperature changes can be surprisingly complex. Dust in the atmosphere absorbs sunlight, warming the upper layers while cooling the surface below. This thermal imbalance can create feedback loops that prolong the storm, making it difficult for conditions to return to normal. Illustrations of rising heat layers and cooling ground temperatures could convey these atmospheric dynamics, helping viewers grasp the delicate interplay that keeps the storms alive. Mars becomes a world with its own rhythms, driven not by moisture like Earth storms but by dust, solar heating, and atmospheric circulation. One of the most breathtaking aspects of Martian dust storms is their vertical reach. Some storms push dust more than 60 kilometers into the atmosphere, creating hazy layers that stretch far above the highest peaks. Visuals could show Olympus Mons, the solar system's tallest volcano, disappearing beneath a thick blanket of suspended particles, its massive silhouette fading as dust rises higher and higher. Satellite data overlays might reveal the altitudes reached by these storms, highlighting their unprecedented scale compared to anything seen on Earth. The towering haze can linger for weeks, dramatically altering how sunlight scatters across the planet. As dust storms escalate, the planet's albedo, its reflectivity, changes significantly. A normally bright surface becomes muted, its reddish tone washed beneath a grayish-brown fog. Scientists have observed that in some global storms, the planet reflects less sunlight overall, absorbing additional heat that slowly destabilizes atmospheric layers. A visual fade from a bright global image to a darker, muted one could emphasize this transformation. These shifts are not merely cosmetic, they influence the planet's climate and energy balance, making dust storms both an environmental and climatic force. Even more fascinating is how dust storms influence the Martian seasons. Large storms often emerge during southern hemisphere summer, when Mars is closest to the Sun. The increased solar heating triggers stronger winds, which in turn lift more dust, setting off chain reactions that can give rise to global storms. A time-lapse visualization could show Mars circling the Sun, with seasonal temperature maps highlighting the conditions that prime the planet for massive dust events. Such animations reveal the deep connection between Mars's orbit, its axial tilt, and the storms that sweep across its surface. These storms also shape the landscape over time. While the winds themselves may not be strong enough to carve rocks dramatically, the persistent movement of fine grains gradually polishes surfaces, fills depressions, and exposes new layers. Visuals could show rocks before and after dust exposure, illustrating how subtle yet constant abrasion alters their appearance. Dunes shift slowly, etched by tiny particles that behave like liquid waves on a frozen sea of rust. Although these changes occur over years, animation can compress time to reveal the relentless reshaping of Mars's terrain. Robotic explorers face unique challenges during these events. Dust can obscure cameras, jam moving parts, and reduce visibility for navigation. A scene depicting a rover slowly turning its lenses toward a dim horizon smothered in haze could convey the eerie atmosphere of a storm. Data readouts showing decreasing solar power or rising dust sensor alerts reinforce the sense of isolation as the machine endures the storm. Opportunity's final weeks, hidden beneath the shadow of a massive global storm, offer a silent testimonial to the power of Martian dust. Humans would face even greater risks. A visualization of a hypothetical habitat under stormy conditions could show how dust accumulates on equipment, reduces power generation, and stresses life support systems. Airlocks, ventilation units, and radiators would require constant maintenance. The dust itself, fine, clingy, and potentially chemically reactive, poses hazards when it infiltrates machinery or interacts with water sources. Showing astronauts brushing dust off suits or struggling to maintain equipment highlights how unforgiving even a thin Martian atmosphere can be when filled with suspended particles. Martian dust storms also affect the planet's color from orbit. During clear periods, the rust-red surface dominates, but during global storms, the entire planet appears shrouded in a faint yellow or pale orange glow. Satellites watching Mars from millions of kilometers away record this change as the planet's disk becomes uniform, losing its contrast and landmarks. Visuals could switch between clear season and storm season global images, showing the astonishing difference in visibility. Mars becomes a world wrapped in a dusty cocoon, almost unrecognizable from its usual appearance. A fascinating feature of these storms is how long they can last. Some regional storms persist for days, while global ones can endure for months. Layers of dust remain suspended high in the atmosphere long after the storm's core subsides. A timeline visualization could display a storm forming, intensifying, spreading, then decaying slowly, with suspended particles lingering far beyond the storm's peak. This extended aftermath demonstrates that dust storms leave a long shadow over Martian conditions, influencing climate and visibility long after the winds quiet. Scientists have learned that these storms also contribute to the global dust cycle, redistributing particles across the planet. Dust lifted in one region may not fall for thousands of kilometers, settling in areas far removed from its origin. This contributes to the uniform coating of fine dust that blankets much of Mars's surface. Visuals depicting dust trajectories using animated particle streams could show how these grains travel, swirl, and eventually descend. Mars becomes a world of constant motion even if the movement is too subtle for human senses to detect directly. Dust storms also interact with Mars's thin carbon dioxide ice caps. When dust settles on the polar regions, it darkens the surface slightly, absorbing more sunlight and accelerating sublimation. This process affects seasonal changes and contributes to atmospheric pressure variations. A visualization of dust settling on bright ice, followed by gradual dimming of the reflective surface, could highlight this subtle but significant effect. It reveals how interconnected Mars's systems are, with dust acting as a bridge between atmosphere, climate, and surface. Another dramatic effect of dust storms is the electrical activity that can arise within them. Some models suggest that friction between particles may generate static charges, possibly even sparks or faint discharges. Although direct evidence is still being gathered, the concept adds another layer of mystery to Martian storms. A visual animation of dust grains colliding and illuminating with soft electric glows could bring this speculative but fascinating phenomenon to life. Even without lightning as seen on Earth, the idea of charged storms adds depth to Mars's atmospheric drama. These storms also offer clues to Mars's ancient past. Geological evidence suggests that dust has played a role in shaping surface features for millions of years. Sedimentary layers composed of fine particles tell stories of ancient winds, shifting climates, and long cycles of atmospheric change. By studying current storms, scientists gain insights into the processes that shaped Mars when it had thicker air and possibly flowing water. Visuals connecting modern storms to ancient landscapes could help viewers understand this long-term evolution. A particularly striking aspect of Martian storms is how differently they appear depending on perspective. From orbit, they look like swirling mists stretching across continents, but from the ground, they manifest as a blinding haze where visibility drops to just a few meters. Showing both viewpoints side by side creates a compelling contrast. The same storm becomes two entirely different experiences, expansive and majestic from above, intimate and disorienting from below. This duality enhances our understanding of Mars's atmospheric complexity. These storms can also create temporary weather anomalies. For instance, temperature inversions may form, where warmer air sits above cooler layers, trapping dust beneath and prolonging the storm's duration. Visual cross-sections of the atmosphere could show layers of warmth and cold shifting during a storm cycle. These unusual patterns have no direct equivalent on Earth, reminding us that Mars's weather follows its own alien logic, shaped by conditions entirely unlike those on our home planet. Even after a storm fades, the world it leaves behind is transformed. Fresh layers of dust settle unevenly, accentuating ridges, filling cracks, and altering the appearance of the terrain. Craters may appear softer, dunes smoother, and rocks more muted in color. A visual reveal showing before and after landscapes highlights how storms repaint Mars subtly but comprehensively. These changes accumulate across years, giving the planet its dusty, uniform complexion. Martian dust storms also influence future exploration plans. Engineers design landers, habitats, and vehicles with storm resilience in mind. Solar panels must be tilted or cleaned, instruments safeguarded, and materials chosen to withstand abrasion. Visuals of design schematics could show how technology adapts to storm conditions, revealing the intricate planning required to survive on a world where dust is not a nuisance but a defining environmental force. Each design choice tells a story of adaptation. The dramatic nature of these storms also captures the imagination of the public. They become symbols of Mars's untamed power, a reminder that despite its beauty, the planet remains merciless and unpredictable. Visuals of swirling storms viewed from space, combined with close-up footage of rovers enduring their dim shadows, create an emotional narrative that blends danger with wonder. These storms remind us that Mars is alive, not biologically, but atmospherically, constantly shifting and evolving. In the end, Martian dust storms serve as a powerful representation of the planet itself, vast, mysterious, breathtaking, and challenging. They reveal a world where the simplest particle can rise to become part of a planet-sized phenomenon. Visually, scientifically, and emotionally, these storms transition the story from ancient fascination to modern understanding, bridging the gap between imagination and reality. They remind us that Mars is not a still, dead world but one animated by forces that demand respect from anyone who seeks to explore its windswept plains. Detail the immediate hazards dust storms pose to missions and potential human habitats, like solar panel degradation and communication disruption. Detail the immediate hazards dust storms pose to missions and potential human habitats, like solar panel degradation and communication disruption, by first imagining how a small, gentle swirl of dust on Mars can quickly become the seed of a massive atmospheric event that engulfs entire regions. On a planet where sunlight is already a scarce resource, any additional dimming becomes a critical issue. As these storms thicken the sky with fine particles, solar panels that spacecraft and habitats rely on begin gathering layers of dust that drastically reduce energy production. Without sufficient power, heaters fail, instruments shut down, and batteries drain faster than they can recharge, turning a minor inconvenience into a mission-threatening obstacle. Even robotic explorers that were designed to withstand harsh conditions struggle when they are deprived of the energy needed for basic survival tasks. Making dust accumulation more than a cosmetic problem, it becomes a decisive environmental force that determines life or death in the silent Martian wilderness. These storms also carry static electricity that builds as particles collide and swirl in turbulent winds, creating unpredictable electromagnetic disturbances. For delicate electronics, these disturbances can cause glitches, sensor errors, or even permanent damage, especially when equipment has no natural protection from an atmosphere as thin and dry as Mars. Communication systems, which rely on sensitive receivers to transmit messages through deep space, become vulnerable to interruptions or distortions in signals. When astronauts would one day depend on uninterrupted links to Earth and navigation systems, even a momentary loss of communication could pose safety risks. The storms therefore challenge not only hardware but the stability of mission-critical information flow across millions of kilometers. Additionally, the dust itself is so fine, almost like smoke, that it seeps into every tiny crack and opening, threatening to infiltrate mechanical joints, seals, and airlocks. Over time, these infiltrations accelerate wear and tear, making machines stiff or jammed. Rovers that rely on wheels, robotic arms, and sampling drills face increasing mechanical resistance, while human habitats would require constant maintenance to prevent dust from entering living spaces. With each storm, machines are forced to work harder against abrasive particles that grind down surfaces and alter the performance of essential moving parts. Even specially engineered components cannot completely withstand the cumulative effect of millions of microscopic grains pushed relentlessly against them by Martian winds. The reduced visibility during these storms poses yet another hazard, not just for navigation but for situational awareness. A thick atmospheric haze makes it difficult for rovers to identify hazards in their path, properly assess terrain, or align instruments that depend on optical clarity. For future astronauts, venturing out in such conditions would be risky, as objects mere meters away could disappear behind an orange blur. Landing missions, which require precise visual and sensor data, risk catastrophic failure if a storm unexpectedly shifts during descent, obscuring the surface and interfering with landing thrusters or altimeters. When dust coats radiators and thermal systems, it hinders heat regulation, which on Mars is already a delicate balance. Too much trapped heat can cause systems to overheat, while too little can freeze vital components. As dust storms envelop a habitat or rover, they can create zones of thermal instability that stress materials and onboard systems. Over several sols, this thermal imbalance can worsen, creating a cycle of degradation that threatens to compromise equipment not designed to endure such drastic temperature disruptions. The storms also challenge mission planners by creating unpredictability. While some storms are regional and short-lived, others can grow into planet-encircling events that last for weeks or months, reducing sunlight everywhere and cutting off visual monitoring. These global storms disrupt long-term scheduling for scientific operations, rover traverses, drilling attempts, and power budgeting. Instruments that depend on direct sunlight for calibration lose accuracy, experiments requiring stable lighting conditions must pause, and surface missions need to shift into survival mode. This unpredictability complicates every aspect of operations, increasing the risk that a mission may encounter dangerous scenarios with little warning. Dust storms also pose indirect threats by altering atmospheric density. Although Mars' atmosphere is thin, changes during a storm can affect aerobraking maneuvers for spacecraft orbiting the planet. If density increases unexpectedly, spacecraft can experience more drag than planned, forcing corrections to prevent orbital decay. If density drops, planned maneuvers become inefficient or fail to achieve desired positioning. This means that even orbiters far above the surface must adapt to the atmospheric chaos kicked up by dust storms below. For human habitats, the loss of solar power may require reliance on nuclear reactors or alternative energy sources, but even these systems face challenges. Dust accumulation can affect air intakes, heat vents, and external sensors. If these structures are not constantly cleared or monitored, the habitat risks unbalanced internal pressure, reduced oxygen production efficiency, or compromised water recycling. Every system becomes more fragile when constantly fighting against a planet-wide blanket of dust. Inside the habitats, fine dust that enters living quarters poses health risks as well. The particles, rich in toxic perchlorates, could irritate lungs or skin if not properly filtered out. Over long periods, exposure could cause inflammation or respiratory issues, making air filtration a top priority. However, the very filters meant to keep astronauts safe can clog faster during storms, requiring more frequent replacements and adding to the strain on resources. Communication disruption during storms also affects Earth-based coordination. Delayed data, partial downloads, or signal loss during critical operations means mission control is left with gaps in information, making it harder to issue safe and accurate instructions. This delay forces missions to operate more autonomously, which increases the difficulty for rovers and early habitats that are not yet capable of independent decision-making at the level humans can provide. Astronauts performing extravehicular activities would face extreme risks if caught in a dust storm unexpectedly. Reduced visibility could cause them to lose orientation, while abrasive particles hitting their suits could wear down outer layers faster. Suit joints and helmet visors might accumulate dust that reduces mobility or visibility. The danger of losing the path back to the habitat or being unable to navigate back safely would rise dramatically. Dust accumulation on sensors is another ongoing hazard. Cameras, atmospheric monitors, and scientific instruments can become partially blinded or blocked. When the storm clears, some sensors may remain coated with dust, requiring cleaning methods that have yet to be fully perfected for Martian conditions. This means storms often leave long-term consequences even after the winds settle. The storms also make in-situ resource utilization, such as extracting water from soil or producing oxygen, more difficult. Dust can contaminate samples, degrade equipment used for extraction, or interfere with chemical processes. If Mars is to support human life, these systems must be robust, and dust storms push them to their limits. Navigation systems relying on solar position sensors or visual markers become unreliable during storms. Without clear reference points, autonomous systems must depend on internal mapping that might not account for new obstacles or changing terrain conditions. This makes travel slower and riskier, reducing mission efficiency. The storms also pose a psychological challenge. For astronauts living in a habitat for months or years, a long storm that darkens the sky could create feelings of isolation or confinement. The inability to leave the habitat, combined with the eerie dim orange glow, may increase stress levels and affect overall mental health. Maintaining morale under such conditions becomes an essential part of mission success. Rovers that depend on sunlight, like the Late Opportunity rover, face existential risks when storms block light for too long. Opportunity's final downfall came from a planet-encircling storm that deprived it of power. This remains one of the clearest demonstrations of how dust storms can bring even the most resilient robots to silence. Landing future supply ships during a storm would be nearly impossible. Visibility issues, shifting atmospheric density, and dust-laden winds all combine to create dangerous landing conditions. Supplies may have to wait in orbit until storms clear, delaying critical missions and complicating timetables. Engineering solutions, such as self-cleaning solar panels or storm-hardened habitats, are still in development. But even the most advanced designs cannot fully eliminate all risks. Mars storms are too vast and unpredictable, forcing designers to accept that some level of vulnerability will always remain. Scientists continue studying how these storms form and evolve, but mysteries remain. Some storms grow unexpectedly large, while others dissipate before reaching maturity. Until predictive models improve, missions will face uncertainty, adapting in real time to a dynamic Martian environment. For future colonists, preparing for months-long storms requires planning for food, power, water, and psychological resilience. Every storm becomes a test of preparedness, one that could determine whether a settlement survives or struggles to maintain stability. Dust storms also reshape the environment by moving sediment across the surface, slowly altering landscapes over time. These changes can affect rover paths or expose new geological features, meaning storms act as both a threat and a transport mechanism for science. Understanding these immediate hazards helps reveal that living on Mars is far more complex than romantic visions suggest. The dust storms are not rare anomalies, they are a defining feature of the Martian climate. Surviving them requires technological endurance, careful planning, and the ability to adapt to a world shaped by swirling, persistent winds. Despite the dangers, each storm teaches us more about this restless planet, slowly guiding us toward safer exploration. And while the hazards are immense, so too is our determination to face them, one storm at a time. Shift focus to how these storms reveal deeper truths about Mars's thin atmosphere and its interaction with the surface by first understanding that the very existence of such enormous storms on a planet with so little air seems paradoxical at first glance. Mars's atmospheric pressure is less than 1% of Earth's, a whisper of a sky that should, in theory, be too weak to lift dust, let alone drive winds strong enough to produce storms large enough to swallow the planet. Yet these storms demonstrate how even a thin atmosphere, when combined with vast stretches of loose dust, powerful temperature contrasts, and subtle seasonal patterns, can unleash forces that reshape the landscape. They remind us that Mars is not just static and silent but alive with slow-motion fury, revealing a world where physics behaves in ways both familiar and alien. Through these storms we begin to understand that Mars's seemingly fragile atmosphere is still dynamic, driven by the delicate balance between sunlight, surface materials, and the planet's long-lost water-rich past. These storms expose how heat moves across the Martian surface, showing scientists that even tiny differences in temperature can create sweeping movements of air. Because there is so little atmosphere, heat from the sun doesn't spread evenly, causing strong gradients between warm and cool regions. These gradients, in turn, generate winds that race across plains and canyons, picking up the finest particles and lifting them high into the sky. The thinness of the atmosphere means those particles linger, creating a global haze that dims the already weak Martian sunlight. Researchers have learned that Mars's climate is governed not by dense atmospheric currents as on Earth, but by small impulses amplified across a planet covered in millions of years of accumulated dust. Every storm becomes a natural experiment, highlighting how equilibrium on Mars is always precarious. Storms also reveal the ways Mars still responds to seasonal cycles, even though it no longer has the thick atmosphere or flowing water that once shaped its hills and valleys. During the southern hemisphere's summer, Mars receives more sunlight due to the planet's elliptical orbit, creating conditions ripe for storm growth. Dust becomes superheated during the day and rapidly cools at night, driving turbulence that lifts more and more particles into the air. These seasonal swings show us that Mars still has a kind of weather rhythm, one dictated by the remnants of its ancient climate and the fragile atmospheric system it has managed to retain. By observing dust storm behavior across multiple Martian years, scientists gain insight into the global energy balance that defines the planet today. The storms also reveal how Mars's surface interacts with the atmosphere in a constant exchange of materials. Unlike Earth, where vegetation and moisture bind much of the soil, Mars's surface is loosely packed and incredibly fine due to billions of years of erosion without rain. When winds blow, the surface literally becomes airborne, transforming landscape into atmosphere. This shows that Mars's climate and geology are deeply intertwined. Any change in one immediately affects the other. The atmosphere transports dust that can darken ice caps, alter how much sunlight they absorb, and contribute to longer-term climate cycles. In this way, the storms function as conveyors that continually reshape albedo variations across the planet, tying together surface darkness, atmospheric heat, and weather intensity. Storms highlight the persistent presence of static electricity generated by friction between dust particles, offering clues about how electricity might build up in the thin air. This static generation has significant implications for chemistry on the surface because it may help break apart certain molecules or trigger reactions that are otherwise unlikely in such a cold, dry environment. Some scientists speculate that electrified dust could influence the breakdown of organics or contribute to the formation of reactive compounds like perchlorates. Thus, dust storms do more than move material, they might be quietly shaping the chemical behavior of the planet, giving Mars a kind of atmospheric laboratory that has been running for eons. The storms also serve as reminders of how much Mars has lost. The thin atmosphere that struggles to hold heat and pressure was once thick enough to sustain rivers, lakes, and perhaps a more temperate environment. When researchers observe how dust storms heat the atmosphere slightly as particles absorb sunlight, They see echoes of what a denser atmosphere might have once maintained on a larger scale. Today, the effect is temporary and minimal, but in the past, similar heat-trapping mechanisms may have influenced climate stability. By studying how current storms retain and redistribute heat, scientists gather clues about the thermal processes that might have shaped ancient Mars long before it became the desert-like world we see now. Dust storms also reveal the efficiency with which the Martian atmosphere circulates material across vast distances. Particles lifted from one region can settle halfway around the planet, proving how interconnected the entire system is despite its thinness. This redistribution provides valuable data on global wind patterns and the slow seasonal migrations of suspended dust. Observations show how storms can darken one hemisphere while brightening another, creating feedback loops that influence temperature and weather. These patterns allow scientists to refine atmospheric models and better understand how Mars maintains its equilibrium despite extreme pressure and temperature fluctuations. Mars's storms also reveal the impact of energy from sunlight on atmospheric dynamics. Because the atmosphere is so thin, even small amounts of solar heating can trigger large reactions. As dust absorbs sunlight, it warms the surrounding air, creating rising currents that expand storm boundaries. This creates a self-feeding cycle in which storms grow larger simply because they already exist, expanding until something in the environment breaks the feedback loop. Understanding these energy exchanges helps researchers identify the thresholds at which storms begin, intensify, and eventually collapse. It also shows that Mars, while dramatically different from Earth, operates under the same universal physical laws, just with different outcomes. The way storms obscure sunlight reveals how fragile Mars's energy balance is. When sunlight drops even slightly, the surface cools rapidly, influencing everything from atmospheric pressure to local winds. A storm that blocks sunlight on one part of the planet can cause colder temperatures that alter pressure systems elsewhere. This interdependence shows how Mars operates like a global machine in which every component, from the poles to the equator, responds to even minor disruptions. By observing how storms shift the balance of light and shadow, scientists uncover deeper truths about how much Mars depends on sunlight not just for energy, but for atmospheric stability itself. Storms also highlight the layers of dust that blanket the surface, revealing how much of Mars's modern appearance is tied to aeolian processes, those shaped by wind. When storms strip dust from certain regions, the darker basalt beneath becomes visible, temporarily altering surface albedo. In other areas, storms deposit thick coatings of dust, hiding geological features and revealing how transient Mars's visible surface really is. These changes act like natural markers, providing visual clues for researchers studying erosion rates, sediment transport, and long-term surface transformation. The storms also point to the existence of tiny dust particles that behave differently than larger grains. Some of these are so small they remain suspended for weeks or months, demonstrating how microscale properties can influence planet-scale phenomena. Understanding these particles helps scientists interpret how Mars's atmosphere forms layers, haze bands, and long-range dust plumes. It also offers clues about the composition of the surface, since the most easily lifted dust likely represents materials that have been continually broken down by geological processes. These storms reveal the remnants of Mars's once active geology. Many dust particles originate from ancient volcanic eruptions, impacts, or mineral breakdowns, meaning each storm carries with it fragments of Mars's deep history. When particles settle, they leave clues about the rocks and minerals from which they came, turning the entire atmosphere into a constantly moving archive of geological information. By analyzing dust composition during storms, scientists essentially read a mobile library of Mars's past states. The storms also show how little protection Mars has from space. Without a strong magnetic field or thick atmosphere, Charged particles from the Sun interact directly with the surface and upper atmosphere, influencing storm formation. Solar radiation can energize the atmosphere just enough to help dust lift off the surface, demonstrating how intimately Mars is connected to the behavior of the Sun. This relationship helps researchers trace how solar activity might have contributed to atmospheric loss over billions of years. Dust storms reveal the disconnect between surface weather and global climate. While storms can be massive, they are not necessarily indicators of long-term climate change. Instead, they represent short-term disturbances in a delicately balanced system. By contrasting present-day storms with sedimentary layers that record ancient ones, researchers begin to understand how stable or unstable Mars's climate has been over geological timescales. This helps them piece together whether Mars ever experienced extended warm periods or whether its climate has always oscillated around cold, dry conditions. In studying storms, scientists also observe how moisture behaves on Mars. Though the planet is mostly dry, trace amounts of water vapor interact with dust, sometimes helping particles cling together or influencing how they absorb sunlight. Dust particles can also provide nucleation sites for frost, affecting surface hydration cycles. These interactions reveal how even minimal water plays a role in shaping atmospheric behavior. Storms also bring attention to atmospheric escape, the process by which Mars continues to lose gases to space. As storms lift particles high into the atmosphere, they may influence how easily certain molecules drift toward the upper layers where solar wind can strip them away. Observations during storms help researchers measure how active this escape process still is, and how it may have contributed to Mars's dramatic atmospheric thinning over billions of years. The swirling movement of dust also allows scientists to map thermal tides, atmospheric waves created by sunlight heating the surface. These tides act as invisible scaffolding around which storm patterns form. By examining how storms interact with thermal tides, researchers gain insight into the deeper structure of the Martian atmosphere, revealing how pressure waves move, break, and reform in ways that drive weather cycles even in the absence of oceans. Dust storms also show how Mars's two moons, Phobos and Deimos, may subtly influence the atmosphere through gravitational effects. Although tiny compared to Earth's moon, their rapid orbits tug gently on the atmosphere, and storms help highlight these small perturbations by amplifying atmospheric motion that might otherwise remain hidden. This creates a complex dance between the planet and its moons, one that scientists are still learning to decode. The storms reflect how Mars responds to long-term orbital changes. Over tens of thousands of years, variations in tilt and orbital shape influence how much sunlight reaches the poles and equator. Dust storm frequency and intensity may rise or fall according to these cycles, making storms key indicators of Mars's climate rhythms. Understanding this connection allows researchers to interpret ancient records and predict future atmospheric behavior. The way storms settle also reveals how landscapes evolve. Dunes migrate, crater floors fill with dust, and rock layers become buried or exposed. These changes tell a slow, sweeping story of geological transformation driven almost entirely by air, something that distinguishes Mars from Earth, where water plays the dominant shaping role. Storms act as sculptors over millions of years, carving and covering landscapes in a gradual but relentless process. Storms also show how Mars's surface materials differ chemically from Earth's. The red dust contains oxidized iron, giving Mars its signature color. Studying how this dust moves during storms gives clues about the distribution of iron-rich minerals and helps decode the oxidation history of the planet. This, in turn, helps explain why Mars's environment became so dry and chemically harsh. By tracking storms, scientists observe how the planet's horizons shift, creating different views of mountains, valleys, and plains depending on atmospheric clarity. This variability reveals how much the Martian atmosphere impacts visibility and makes it clear that any future exploration, robotic or human, must adapt to constantly changing conditions. Scientists must factor atmospheric clarity into landing site selection, operational planning, and long-term mission success. Lastly, dust storms reveal just how alien Mars truly is. They expose a world caught between the remnants of a once habitable past and the cold stillness of its present. The storms serve as constant reminders that Mars, for all its similarities to Earth, operates under a unique set of environmental rules shaped by thin air, ancient geology, and delicate atmospheric forces. Through the study of these storms, we uncover layer after layer of Martian complexity, each one a window into a planet that still holds countless mysteries beneath its shifting veil of dust. Explore the long-term effects of dust storms on Mars's climate and the slow erosion of its once denser atmosphere by first recognizing how each storm, whether small or planet-encircling, contributes to a steady redistribution of dust that subtly modifies the planet's energy balance over time. Every time sunlight hits a dust-laden Martian sky, a portion of it is absorbed and re-radiated as heat, warming the upper atmosphere more efficiently than the ground itself can manage. This imbalance affects pressure gradients, which in turn influence the frequency and strength of future storms. Over thousands or millions of years, such feedback loops may have played a part in transforming Mars from a planet with flowing water and thick air into the thin, fragile world we see today, where storms simultaneously shape and reveal the remnants of a climate in slow decline. As dust storms circulate, they lift fine particles into the upper atmosphere where they can interact with solar radiation and changing thermal patterns. These interactions slowly influence atmospheric structure by altering how heat is distributed across different altitudes. When dust heats the atmosphere, it increases the height at which certain winds form, subtly reshaping circulation cells that span the entire planet. These shifts might seem small when observed over a single year, but across many cycles they contribute to long-term variability, gradually adjusting how heat moves from the equator to the poles. Scientists believe that these persistent disruptions may have helped accelerate atmospheric thinning by weakening the stability of the upper layers, making them more vulnerable to solar wind stripping. Dust storms also change the reflective properties of the planet's surface. When storms strip dust away from some regions, they expose darker material that absorbs more sunlight, causing localized warming. Conversely, when storms deposit dust in thicker layers, they brighten other regions, causing cooling. This constant push and pull creates a patchwork of temperatures across the surface that influences wind patterns and pressure systems. Over vast geological timescales, these temperature differences may have guided the evolution of Mars's weather cycles, increasing the planet's dependence on dust for climate regulation in the absence of oceans or thick clouds. This deep reliance on dust-based feedback loops marks a significant shift from the wetter, warmer environment that once defined ancient Mars. The storms also affect the polar caps, which play a major role in regulating atmospheric pressure through seasonal freeze-thaw cycles of carbon dioxide. When dust settles on the ice caps, it darkens their surfaces, causing them to absorb more sunlight and sublimate faster. This increases the amount of CO temporarily released into the atmosphere, raising pressure slightly until the next cooling period reverses the process. Over millions of years, the cumulative effect of dust-altered ice cap cycles may have reduced the planet's ability to maintain stable atmospheric layers. As darkened regions absorbed more heat, they fueled more evaporation, more pressure swings, and ultimately more instability within an already fragile climate system. Dust storms lift particles high enough that they can interact with ultraviolet radiation from the sun. These interactions trigger chemical reactions that break apart molecules that would otherwise contribute to atmospheric thickness. For example, dust particles may accelerate the breakdown of water vapor into hydrogen and oxygen, with the lightweight hydrogen escaping into space. Though the process is subtle on short timescales, over billions of years it contributed to Mars's loss of water and the thinning of its atmosphere. These small chemical imbalances induced by dust and sunlight left Mars progressively more vulnerable to solar wind erosion, creating a feedback cycle where storms indirectly aided the escape of gases that once made the planet more Earth-like. The fine dust suspended in the atmosphere also alters thermal tides, giant planetary waves driven by daily heating and cooling. When dust changes how these tides propagate, it alters the timing and intensity of winds that influence which atmospheric particles reach the exosphere, the region where gases can be stripped away by solar wind. Over time, these modified tides can enhance atmospheric loss by pushing certain molecules upward more efficiently. This seemingly gentle, cyclical breathing of the atmosphere creates subtle but persistent avenues for escape, contributing to the slow unraveling of an atmosphere that was once thick enough to support liquid water on the surface. Dust storms reveal that Mars's present climate is not simply weak, it is decaying in slow motion. While Earth's atmosphere recycles itself through weather, oceans, and tectonics, Mars's does not. Instead, its storms lift and redistribute the same dust again and again, slowly grinding minerals finer and finer, making them easier to loft and harder to settle permanently. With each storm, the surface becomes more finely powdered, and the atmosphere becomes more dust-rich. This gradual enrichment of airborne dust affects how much sunlight reaches the ground, making certain regions cooler and altering the potential for frost, seasonal co-deposits, and localized atmospheric cycles. Over vast timescales, this slow accumulation may reinforce the planet's tendency toward cold, dry conditions. Long-term storm activity may also have played a role in the retreat of ancient Martian lakes and rivers. As storms repeatedly swept the surface, they carried away lighter sediments and left behind heavier or chemically altered ones. These processes gradually transformed the landscape into one where water had fewer opportunities to pool or flow. Atmospheric dust also interfered with the long-term warming potential of greenhouse gases by increasing reflectivity in key regions and reducing the amount of solar energy reaching the ground. Even slight reductions in average surface temperature would have accelerated the freezing and sublimation of water sources, reinforcing the planet's march toward desiccation. Dust storms influence the long-term behavior of carbon dioxide and water ice trapped beneath the surface. When dust blankets certain areas, it insulates them, preventing sublimation and preserving ice reserves. In other areas, dust removal exposes ice to sunlight, causing rapid sublimation. These alternating patterns of protection and exposure help shape Mars's climate cycles. Over geological periods, they contribute to shifts in ice distribution that reflect massive climate swings, cold epochs that bury ice under dust, and warmer epochs that expose it. These fluctuations reveal that Mars's climate is not static but oscillates on timescales much longer than a human lifespan, with dust storms as one of the key drivers. The storms are also linked to long-term erosion, slowly breaking down rock surfaces with their abrasive particles. This erosion is far slower than that caused by water on Earth, but over billions of years it has reshaped entire landscapes. The resulting fine dust becomes part of the atmosphere, reinforcing the cycle of suspension, deposition, and resuspension that keeps Mars's climate tied to its own eroded past. This process means that Mars's atmosphere is continually infused with the relics of its geology, serving as both the carrier and the product of planetary change. Dust storms contribute to the gradual thickening of regolith, the loose soil covering bedrock, making the surface increasingly dusty over time. As regolith layers grow deeper, they affect temperature retention and the reflectivity of the ground. These changes influence long-term climate behavior by altering the way heat is stored and released. In a sense, Mars's surface becomes a vast climate archive and climate engine simultaneously, shaped and reshaped by the invisible hands of millions of storms over countless centuries. The pervasive dust also plays a role in shaping Mars's ancient climate record, which scientists read through sedimentary layers, ice cores, and mineral composition. Long-term storm activity leaves behind stratified dust deposits that serve as snapshots of climate conditions across eras. By analyzing these layers, scientists learn how storm frequency has changed over time and how these variations correlate with shifts in atmospheric thickness, surface temperatures, and orbital patterns. Dust storms thus become a geological signature, an imprint left by a planet whose weather is written in dust rather than water. Storms may have also influenced the planet's ability to maintain greenhouse gases. Some particles lifted during storms chemically interact with carbon dioxide or other trace gases, trapping them in the surface or breaking them apart. Over billions of years, these interactions could have contributed to the decline of gases necessary to warm the planet. Without a strong greenhouse effect, Mars's climate continued to cool, reinforcing the planet's long path toward atmospheric collapse. Dust storms also reveal how sensitive Mars is to solar cycles. During periods of high solar activity, increased radiation heats the upper atmosphere, making it easier for gases to escape. Storms that lift dust high into these energized regions amplify this effect. Over long timescales, this coupling between solar cycles and dust activity has slowly stripped Mars of its atmosphere. The storms act like channels that guide molecules upward into vulnerable regions where solar wind can carry them away forever. The dust storms affect Mars's long-term climate by altering the stability of certain mineral phases on the surface. Minerals exposed to sunlight during storms may undergo photochemical reactions that release or absorb gases. These reactions, though slow, can subtly alter atmospheric composition. Over geological periods, they may have contributed to the decline of volatile gases or influenced the chemical pathways that preserved or destroyed organic molecules on the surface. Dust storms also play a role in shaping Mars's thermal inertia, the ability of the surface to store heat. Regions repeatedly buried under dust become more insulating, cooling down rapidly at night and warming slowly during the day. These changes influence local air movement, which feeds into larger climate cycles. Over time, the redistribution of dust alters not only the local environment but the planet's overall thermal behavior. The storms illuminate how Mars's climate has reached a kind of standoff with itself. Its thin atmosphere cannot sustain long-term warming, yet the storms triggered by that same atmosphere continue to reshape the planet. This paradox, fragile air producing immense storms, is one of the keys to understanding how Mars arrived in its current state. It shows that climate decay does not always mean inactivity. Instead, the remnants of Mars's ancient weather systems echo through the storms, carrying the memory of a thicker, wetter atmosphere in their behavior. Over millions of years, dust storms may have influenced the migration of ice from the mid-latitudes to the poles. As dust insulated some regions and exposed others, it shaped where ice could stabilize. This movement of ice reservoirs changed the planet's long-term water distribution, affecting opportunities for erosion, sedimentation, and potential habitability. Dust storms, therefore, have not only shaped the air but also the underground cryosphere of Mars. Dust storms might also have influenced the pacing of ancient climate transitions. In epochs when the atmosphere was thicker, storms might have been different, less intense, but more frequent, or might have interacted with liquid water and clouds in ways impossible today. Studying the long-term evolution of storm patterns gives researchers clues about how Mars moved from warm and wet to cold and dry, suggesting that the storms we see today are the weakened echoes of once much more complex systems. The slow erosion caused by dust storms reveals just how ancient and weathered Mars's geology is. Without plate tectonics or significant volcanic resurfacing, the planet's surface holds scars and dust from billions of years of environmental decay. This makes storms both destroyers and preservers, erasing some features while endlessly redistributing the evidence of past epochs. Over time, this process has contributed to the smoothed, wind-sculpted terrain that characterizes much of the planet today. The storms also play a role in how radiation reaches the planet's surface. By altering atmospheric opacity, they change how much harmful radiation penetrates to ground level. While Mars's atmosphere is too thin to offer significant protection, even minor changes in opacity can influence the stability of chemical compounds on the surface. Over thousands of years, these subtle shifts contribute to the breakdown of sensitive materials, influencing the preservation of potential biosignatures. Dust storms also highlight how Mars's climate lacks the self-correcting mechanisms found on Earth. With no oceans to absorb heat, no thick atmosphere to buffer temperature swings, and no active geological recycling, Mars depends almost entirely on dust storms to redistribute heat and material. This dependence creates a fragile equilibrium, one easily disrupted and slow to recover. Over eons, this instability may have nudged Mars further toward atmospheric decline, reducing the planet's ability to support long-term climatic stability. Ultimately, the long-term effects of dust storms tell the story of a planet losing its breath. Each storm represents a small piece of the puzzle, an atmospheric pulse that slowly weakens over deep time. Through these storms, we see how Mars evolved from a world rich in air and water to one defined by silence, cold, and dust. The storms are both the lingering heartbeat of its ancient climate and the agents that help carry its atmosphere steadily, grain by grain, into the vastness of space. If you'd like, I can continue with part 7 or begin the next segment.